History of Elixir. Elixir is a dynamic, functional language designed for building scalable and maintainable applications. Jose Valim is the creator of Elixir, and his background in Ruby as a core contributor to the Ruby on Rails framework influenced the creation of Elixir. The language was officially announced in 2011 and has since evolved with contributions from the open source community. While there's no concrete code snippet associated with the history of Elixir, it's important to understand that Elixir runs on the Erlang VM, BEM, and it is known for its capabilities in building low-latency, fault-tolerant distributed systems. Elixir's syntax is heavily inspired by Ruby, and it provides metaprogramming capabilities with macros. Its concurrency model is inherited from Erlang, based on actors and message passing. This history provides context for why Elixir looks and behaves the way it does, especially in terms of syntax, concurrency, and fault tolerance. Functional programming paradigm. In Elixir, which is a functional programming language, we focus on writing functions that receive inputs and produce outputs without side effects. This means functions are intended to behave predictably, not depending on or altering any outside state. In this code snippet, we define a module mathutils that contains a function sum, which takes two arguments and returns their sum. This exemplifies a core concept of functional programming, creating pure functions that, given the same input, will always produce the same output without modifying any external state. The function sum doesn't depend on any outside data and doesn't cause any side effects, which means it is a pure function. Features of Elixir. Elixir's concurrency is based on the actor model, where each process communicates with others through message passing. Let's demonstrate a simple example of spawning a process and sending a message to it. In this example, we spawn a new process with a function that waits for a message. Once it receives a message, it prints it out. The send function is used to send a message to the process identified by PID. Installing Elixir. To start working with Elixir, you first need to install it on your computer. Elixir runs on the Erlang VM, Beam, so you'll need to install Erlang before installing Elixir. The installation steps vary depending on your operating system. Below, you'll find the code for installing Elixir on a Unix-like operating system using pre-compiled packages. The given code block is a sequence of commands. This is used for Debian-based Linux distributions, such as Ubuntu. The script downloads a package from Erlang Solutions, installs it, updates the package list, and then installs the Erlang OTP platform and all of its applications. After Erlang is installed, the script installs Elixir. Note that sudo is used to grant administrative privileges for the installation process. Basic Elixir syntax and REPL usage. Elixir's interactive shell, called IEX, is a REPL, read-eval print loop, which allows you to interact with Elixir by typing code and getting immediate feedback. This command starts the Elixir REPL. Once you type it in your terminal and hit enter, you will be in an interactive Elixir session where you can type Elixir expressions and see their results immediately. Elixir's tooling, Mix Hex. Mix is a build tool that provides tasks for creating, compiling, testing your application, managing its dependencies, and much more. The Mix new myapp command is used to create a new Elixir project with a predefined directory structure. It includes configuration files and boilerplate for the new project that follows Elixir's conventions. Running this in your terminal initializes a new Mix project named myapp. Data types: integers, floats, booleans, strings, atoms. Integers are whole numbers without any fractional part. In Elixir, you can also use the underscore character as a separator for readability. The code defines a variable called integer, holding the value 1000. The underscore in 1000 serves to make the number easier to read and has no impact on its value. Basic operators. Arithmetic operators in Elixir are used to perform mathematical computations. The basic arithmetic operators are plus, minus, for addition, subtraction, multiplication, and division respectively. In the code, sum calculates the addition of 5 and 5 resulting in 10. Sub computes the subtraction of 5 from 10, resulting in 5. Mult represents the multiplication of 4 by 5, resulting in 20. And div performs the division of 20 by 5, resulting in 4.0. Note that division always results in a float, even if dividing even numbers. Pattern matching. Pattern matching is one of Elixir's most powerful features, allowing a developer to easily destructure data and assign values to variables. Simply put, pattern matching is Elixir's approach to variable assignment and comparison, using the match operator equals. It is not just about matching left-hand side to right-hand side values, but rather about the left-hand side pattern matching the structure of the right-hand side value. In the first line, we create a list with the elements 1, 2, and 3. In line 2, pattern matching is used to destructure the list into individual elements, where A gets the value 1, B gets 2, and C gets 3. This is confirmed by matching the structure on both sides of the equals sign. In the third line, x equals 1 simply assigns the value 1 to the variable x. Finally, in the fourth line, a tuple 2, 3 is pattern matched to variables y and z, where y becomes 2 and z becomes 3. Immutability. In Elixir, once a variable is assigned a value, the value itself cannot be altered. This is known as immutability. Variables in Elixir can be rebound to new values, but the original value remains unchanged. This concept is fundamental in Elixir and affects how one writes and thinks about code. In the example, list is a variable bound to the value 1, 2, 3. When we modify the list using list.deleteAt, it doesn't change the original list. Instead, it creates a new list without the last element and assigns it to new list. List will still be bound to 1, 2, 3, showcasing immutability in Elixir. Elixir Data Structures, tuples, lists, keyword lists, maps. Tuples are ordered collections of elements. They are written with curly braces and are useful when you want to keep a fixed number of elements together. This tuple contains 3 elements, an atom OK, an integer 42, and a string next. Tuples are indexed starting from 0 and can be accessed using the elms2 function and updated using the putelms3 function. Control structures, if, unless, case, cond. The if structure is one of the most fundamental control structures in many programming languages, including Elixir. It is used to evaluate a condition and execute code depending on whether the condition is true or false. This code checks whether 1 plus 1 equals 2. If the condition is true, it returns maths is correct. If it is false, which in this case is impossible, it would return maths is broken. Anonymous functions and the AND notation. Anonymous functions in Elixir are created using the fn keyword, followed by a set of parameters, the net symbol, and the function body. They are closed over their environment, allowing them to access variables that were in scope when the function was defined. Here, we define an anonymous function that takes 2 arguments and returns their sum. The function is assigned to the variable sum. To invoke this function, we use the dot, followed by parentheses enclosing arguments, as shown in the invocation sum 5, 3, which calls the function with arguments 5 and 3 and stores the result in the variable result. Named functions and modules. In Elixir, named functions are grouped inside modules. A named function is declared using the def keyword within a module and must be inside a module. We use modules to organize functions into separate namespaces. Here's how to define a simple module and a named function within it. In this code snippet, we define a module named greeter using df module. Inside the greeter module, we define a named function hello that takes 1 argument, name. The function simply returns a greeting string interpolated with the name provided. To use this function, we would call greeter hello Alice. File I/O using Elixir. In Elixir, File I/O is managed through the File module, which provides functions to read and write to files. These operations can be performed either synchronously or asynchronously. Let's look at simple synchronous file operations such as reading from and writing to files. The code snippet demonstrates how to write to and read from a file in Elixir using the File module. First, file.write/2 is called to write the string hello world to hello.txt. If successful, the function returns OK. Next, file.read/2 reads the contents of hello.txt. The result is a tuple where OK indicates success and contents is bound to the data read from the file. Lastly, io.puts1 is used to output the contents to the terminal. Processes and process management. In Elixir, processes are lightweight and run concurrently on the Beam virtual machine. The spawn function is used to create a new process by specifying a function to be executed in that process. In this code snippet, spawn is used to create a new process that executes an anonymous function. The function sends a tuple, hello world, to the process that spawned it, self. The PID, process identifier, of the new process is bound to the variable PID. Message passing. In Elixir, processes communicate asynchronously by sending messages to each other. Each process has a mailbox where incoming messages are stored until they are processed. Message passing is a way to achieve concurrency in Elixir. Let's explore this concept with a simple example where one process sends a message to another process. The code defines a module message_demo with a function start, which spawns a new process that runs the listen function. The listen function waits for a message in the format of sender messg. Once it receives a message, it sends a reply back to the sender with confirmation that the message was received. The start function returns the PID, process ID, of the spawned process. The script then sends a hello process message to the spawned process and waits for a reply. If a reply is received, it prints the reply. Otherwise, if no reply is received within 5 seconds, it prints a timeout message. Task module. In Elixir, the task module provides a way to create and manage background work that can be executed concurrently with your application. This is often used for computations that are expensive or tasks that can be run independently. Here, we will see an example of how to start a task and wait for its completion. This code defines a module myModule with a public function async_greet/1, which takes a name and starts a task that runs a greeting function. The greet1 function is a private function that simply prints a greeting message. When async_greet is called, it initiates the greeting task and immediately returns a tuple containing the task struct and a reference. The caller can then use task.await/1 to wait for the task to finish and get its result. In this case, the task's result is the output of the io.puts function. Agent module. In Elixir, the agent module is a simple but powerful abstraction for state management. It allows you to create a separate process to store and retrieve state, offering a clean way to manage shared state in a concurrent system. Agents encapsulate state and provide it upon request, which is especially useful when you want to maintain state across multiple function calls or processes. The code defines a module, myAgent, which uses the agent module to encapsulate state. The startLink function initializes the agent with a default value. The getValue function retrieves the current state from the agent, and the updateValue function updates the state using a provided function. We instantiate the agent with the initial value 42, retrieve this value through getValue, and update the value by incrementing it using updateScourseValue. Each function operates on the agent's state in isolation, promoting safe concurrent access. GenServer. A GenServer is a process like any other Elixir process, and it has its own mailbox. It abstracts the boilerplate code for writing a server in a concurrent environment. The code defines a GenServer with a simple API to get its internal state, which is set at startup. The useGenServer line brings into scope required callback functions. StartLink is called to start the GenServer. Init initializes the state and is called when the server starts. HandleCall handles synchronous calls to the server. When getValue is called by a client, it sends a message to the GenServer, which in turn calls HandleCall with the current state as a response. State management. In Elixir, state management in concurrent programming often involves processes that maintain state over time. An essential building block for this is the GenServer, which is a generic server implementation that abstracts the common patterns of synchronous and asynchronous requests. The provided code defines a simple bank account module that uses the GenServer behavior to manage the state of a bank account balance. The startLink function starts the GenServer with an initial balance. The deposit function is synchronous, using GenServer.call, and the server's handle call function updates the balance by adding the deposited amount. The withdraw function is asynchronous, using GenServer.cast, and the server's handle cast updates the balance by subtracting the withdrawn amount. This code demonstrates encapsulating state within a process and modifying it in response to messages. Supervisors and Applications. In Elixir, supervisors are processes which monitor child processes. They are designed to handle process termination and are an intrinsic part of building fault-tolerant applications. In the code, my supervisor is defined as a supervisor module by using useSupervisor. It has a startLink function that starts the supervisor process. The init function defines the child processes to be supervised, in this case a single worker myWorker. The supervision strategy, one-for-one, means if myWorker crashes, only that worker will be restarted. Erlang OTP. OTP stands for Open Telecom Platform, and it is a set of Erlang libraries and design principles, providing middlewares and tools for building robust, fault-tolerant applications. Elixir is built on top of Erlang, allowing developers to leverage the power of OTP. GenServer is a generic server implementation that makes it easy to build concurrent applications in Elixir. The provided code defines a simple GenServer called example GenServer. It defines two functions for clients, startLink and increment, and implements the necessary callbacks for the server, init, handlecast, and handlecall. startLink starts a new GenServer process with an initial state. Increment increments the state asynchronously using handlecast. Value retrieves the current state synchronously using handlecall. This example encapsulates state within the server process and provides a clear interface for interaction, demonstrating how GenServer abstracts the complexities of concurrent programming. Using Observer to view system. The Observer is a graphical tool for observing the various aspects of an Elixir system, including process lists, applications, and more. It is especially useful for debugging and monitoring a running system. This command is executed in the Elixir Interactive Shell, IEX. The observer.start function comes from Erlang's Observer module, which Elixir can access due to interoperability. When executed, it starts the Observer GUI, from which you can visually inspect the current state of the Elixir runtime system, including process information, network topology, system load, and more. Enumerable Protocol. In Elixir, the Enumerable Protocol provides a set of algorithms that can be used for iterating over collections. Various types like lists, maps, ranges, and streams implement this protocol, allowing them to be traversed and manipulated using functions from the Enum Module. Let's explore how to leverage the Enumerable module with a simple example using a list. The code demonstrates the use of enum.map_2 function, which is part of the Enumerable Protocol. In this example, we have a list 1, 2, 3, and we use enum.map/2 to iterate over each element, applying the anonymous function fnx_x_x_end to each element, and then returning a new list with the squared values. As a result, the output of the code would be a new list 1, 4, 9. The Enumerable Protocol enables this operation on any collection that implements it, not just lists. The Enum Module. In Elixir, the Enum module contains a set of algorithms for iterating, searching, sorting, and manipulating collections. Collections can be lists, maps, ranges, and others that implement the Enumerable Protocol. It provides functions like map, reduce, filter, and more, which are essential for functional programming. Let's explore a simple use case of the Enum module by iterating over a range and finding the sum of all numbers. In the provided code, enum.reduce is a function from the Enum module that aggregates a collection into a single value. The first argument, 1, 10, is a range representing numbers from 1 to 10. The second argument, 0, is the initial accumulator value. The anonymous function fnx_x_end is the reducer. It takes each element x from the collection and the accumulator asser, adding them together. The result, sum, is the total sum of numbers from 1 to 10. Streams. Streams in Elixir are lazy, composable enumerables. This means they are collections that can be enumerated over, but they do no work until it's needed, which is unlike lists, which are eager. This laziness allows for potentially infinite sequences and can be very efficient because computation is deferred and only performed when values are actually needed. Let's see how we can create a stream, add to it, and finally enumerate over it to trigger the computation. In the provided code, we first define a stream using stream.iterate/2, which starts from 0 and creates an infinite sequence by incrementally adding 1 to each successive item. Then, we pipe this stream into stream.take/2, which limits the sequence to the first 10 elements. Finally, we convert the limited stream into a list using enum.toList/1, which forces the evaluation of the stream and generates the actual list 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This step is where the lazy computation of the stream turns into an eager computation, resulting in a finite list. Comprehensions. Elixir comprehensions are a syntactic sugar for looping through enumerables like lists, maps, and others to generate a new collection. They allow for the concise construction of lists from a set of values, filtering, and transformation with less code compared to traditional loops, or using enum.map2 and enum.filters2. This code demonstrates a simple list comprehension in Elixir. The for construct iterates over the list 1, 2, 3, 4, but only includes elements where n3 holds true. For these elements, it calculates n, the square of the number, and includes the result in the new list. Hence, comprehension will hold the value 1, 4, as it contains the squares of the numbers 1 and 2, which meet the condition. Working with lists and maps. In Elixir, lists are collections of elements that can contain any type of data, including other lists. Lists are linked lists, meaning that it's quick to insert and remove elements at the head of the list, but accessing elements is linear in time. This example demonstrates basic list operations in Elixir. We start by defining a list with the elements 3, 2, and 1. Then we create a new list by adding the element 0 to the head. Following, we retrieve the length of the new list. Lastly, we use the enum.withIndex function to create a new enumerable based on new list, with each element accompanied by its index. Reducers and collectibles. In Elixir, reducers are functions that process collections item by item and accumulate a result. The enum.reduce3 function is commonly used to carry out this operation. The code uses enum.reduce3 to sum the values of a list. The first argument is the list 1, 2, 3. The second argument 0 is the initial accumulator, and the third argument is an anonymous function that describes how to combine each element x with the accumulator ac, in this case by adding. The result of running this code would be 6.